A couple of things to let you guys know, we'll be finishing up that little section of 5.1 on exponential functions, and then we'll be moving on into 5.2 logarithmic functions and reminding you guys of those properties. And then we'll move on into what calculus is all about, actually taking the derivative of these guys. So that's my goal for the day. And just to remind you guys, you have your quiz number 8. It's open and ready for you guys to take it. I think it's due on like Saturday. And 5.1 is due Sunday. And then we'll get back into our regular scheme of things as we've just had tests and stuff. So last time, we were looking at exponential functions and the like. And basically, out of these exponential functions, you needed to know that you can have an exponent of anything. However, when you graph these guys, your range is always above the x-axis. You always get positive numbers when you plug in functions into, plug in x's into the exponent of any kind of function and stuff. And there's basically two big formulas you need to know in terms of the compound interest. You got your regular compound interest, which is a equals p times 1 plus r over n raised to nt. This is calculus class, so we do expect you guys to memorize this stuff. P is your principal, r is your interest rate, t is your time, typically measured in years, and n is the number of times a year you compound, and a is the amount of money you get out of the account after so much time. And the other formula you needed to have memorized is if you got the best type of compounding, and the best type of compounding is that compounded continuously, you get that a equals p e to the rt. So, there we go. And so, continuing on. We did a bunch of problems last time, and but we didn't quite finish the thing. So I'm going to pick it up with problem number 4. It stated this, that the concentration C of t of a certain drug in the bloodstream after t minutes is given by the formula C of t equals 0.07 times parentheses 1 minus e to the negative 0.3 t. What is the concentration after 3 minutes? Round your answer to 3 decimal places. All right. Well, this one is honestly not that bad of a problem. Because number one, you just have to analyze your units. And the key to this stuff, all physics, all business, any kind of word problems is pay attention to units. Now, C of t is your concentration of the particular drug that we're playing with here. And t is measured in what? Minutes. All right, that's the main thing right there, making sure your units match up. So they gave me a formula, and my formula is very simply this. C of t is equal to 0.07 times 1 minus e to the negative 0.3 t close parentheses, where what is the concentration after 3 minutes? So they're giving me time equals 3, and it is in minutes. So what am I supposed to do with this problem? Very simply, plug in t. So we're basically looking for what is C of 3. That would be 0.07 times 1 minus e to the negative 0.3 times 3. And so the only way you're going to screw this problem up is if you put it in your calculator poorly. So let's see here. I'll plug in my calculator. This would be 0.7 times parentheses 1 minus the e button is located right above the ln, natural log button. Second e raised to the negative 0.3 times 3. And then I over arrow close parentheses, and I make it look exactly the way it looks like on the form, again using our E button here, and I end up getting the answer of 0.04154012338. However, because of the way they add the answer, and again, I'm trying to set you guys up for the Hawk stuff here, how many decimal places they wanted it? 3 decimal places. So if I round this answer to my 3 decimal places, what would that be? 0.04 and 1, but there's a 5 after 1, so I'm supposed to round it up to a 2. 3 decimal places. Does that make sense? I'll lose you guys anyway. And just pay attention to what they ask for in terms of decimals and stuff. All right. The next one, however, is something, again, you're going to have to use a formula. Find the amount of money that will be accumulated in the savings account if $5,300 is invested at 6% interest for 24 years at an interest is compounded continuously. Round your answer to 2 decimal places. And with money, 2 decimal places is standard for down to the nearest penny. Okay? Well, the key to this problem is very simply reading through the problem, writing any numbers. If you have a savings account where you have $5,300 is invested, that will be your principal. That is $5,300. Your interest rate is 6%, but remember percentages for people who can't do math. What's 6%? 0.06. Your time is equal to 24 years. Time equals 24. But the key to it is the word compounded continuously. Compounded continuously is your special type of compounding formula. And what is that one? A equals P e to the RT. You may know it better from high school as the famous PERT formula. A equals PERT. P e to the RT. So plugging my numbers, and what we're looking for in this problem is how much will accrue. That would be your A, the amount in the account here. So A is equal to 5,300 e to the 0.06 times 24. So putting this one out and typing this in, 5,300 e raised to the 0.06 times 24, and this is money. So I'm going to round it to the nearest penny in terms of 2 decimal places. So now if you can get that 6% account, and if you can afford to let the money sit there for 24 years at 6%, how much money we're going to get in the account? $22,369.69, rounding to the nearest penny, 2 decimal places. Does that make sense? Don't lose you guys anywhere. Questions? All right. So section 5.1, honestly, is reminding you about exponential functions and their properties and 2 major formulas. Okay? That's the big deal. And those 2 major formulas, being business calculus here, is the compounded continuous interest, the PERT formula, and the regular compounding interest, A equals P times 1 plus R over N raised to the NT. Things you guys need to know. All right. So for the next section, section 5.2, we're working on logarithms. Now, logarithms are supposed to be a review to even get into this class, but it's been a while maybe since you used them, so I want to remind you of some of your log properties here. Now, we're going to be focused on, there's the traditional log, which is y equals the log base a of x, and then there's a very special log that we traditionally like to use, and that is y equals the log base e of x, but that log base e, we call that a special log, and what is that called? The natural log of x. ln, log del natural log of x. And at ln, that's that ln button we just saw on the calculator. That is log base e. Okay? Now, remember the purpose of logarithms. Listen up and listen good if you don't remember this stuff. Logarithms got one job in life. Logarithms were defined or created to solve for exponents. So anytime you've got a variable in the exponent that you need to solve for, you want to use logs. Okay? And so when you have this property right here, when you got y equals the log base a of x, this is written in logarithmic form. You can rewrite this guy. It means the exact same thing written in exponential form. And the exponential form of a log, this is the exponential form of a log, is this. You start with the base a, you raise it to the other power y, it equals what you're taking the log of, equals x. It's an equation, a to the y equals x. So this is exponential form and log form. See, because here's the deal. You've been playing around with exponents since around the 4th grade, honestly. So exponents are your comfort zone. You didn't discover logarithms until about, what, the 10th grade or 9th or 10th grade or something like that when they were literally first introduced to you guys. So based upon that, your comfort zone is exponents because you've been using that for years. Logarithms, not so much, but they're very important because they solve for exponents. That's the purpose of why we study these guys, okay? Now, so in a similar sense, if I have here y equals the natural log of x, I can use that and rewrite that in its exponential form. But what is the base, even though we don't write it down here? What's the base on a natural log? What is that base? It's understood to be an e. And I can use the same, and I call this the smiley face definition of logs. It makes it look really use a smiley face. You start with the e, you raise to the side y, and it'll be equal to what you're taking the log of, and that is x. So there's the exponential, the natural log exponential form. Okay, it's e to the y equals x. Okay? Now when it comes to properties and stuff, and again, we're going to be focusing mostly on the natural log with that base e, because that tends to show up in your business and your exponential growth and decay and so many different areas and stuff, especially that compound and continuous and stuff. So for under our learn mode here, all right, here's the deal. For natural logarithms, e to the y equals x is if and only if, what is this equivalent to? E to the y equals x. It's the same thing as y equals the natural log of x. This is the exponential form, this is the log form. But here's the big deal about logs. When it comes to logs, note, you can only take the log of positive numbers. Which means if I got something like y equals the natural log of x, in terms of what kind of numbers, what's my domain of the natural log of x, you can only take the log of positive numbers. So the answer is, the natural log of x is the domain, is the set of answers that is the positive numbers. X, if you got y equals the natural log of x, x has got to be strictly greater than 0. You can't take the log of 0, nor can you take the log of negative numbers. So listen up. Now we've got three things in our repertoire of problems with functions. You can't divide by what number? 0. Big rule, bad. Can't divide by 0. You can't take the square root or an even root of what kind of numbers? Negative numbers. You can only take square root of 0 or positive numbers. And now when it comes to logarithms, you can only take the log of positive numbers. So you got another domain restriction on this stuff. You can only take the log of positive numbers. So there's three restrictions you guys have to focus on when you're playing around with your math. So now, log properties. Now, here's the log properties. Again, this is more a review, but if you go back and look at your exponential properties, there's three exponential properties, and they are this. When I had a to the x times a to the y, when you multiply exponential function with like bases, what do I get to do with the exponents? What's the rule? When I multiply with like bases, what do I get to do with the exponents? I add them. That'll be a to the x plus y. This is the exponential forms here. If I have a to the x divided by a to the y, when I divide, as long as those bases are the same, what do I get to do the exponents? Subtract, top minus bottom. That'll be a to the x minus y. And the last one was this. If I have a to the x raised to the y, I got something raised to a power and then raised to another power. What do I get to do with the powers? Multiply. These were my exponential properties from many, many years ago. These are the exponential properties. Now, as I mentioned to you guys, logarithms solve for exponents. So they are literally the inverse of the exponential functions, but they solve for exponents, so they're going to have the same properties. And these are the properties. When I take the natural log, we're focusing on natural log in this section, natural log of multiplication. But the natural logs are actually solving for the exponents. And when you're multiplying exponents, like bases, that natural logarithms will turn into addition. So these exponents, when you're multiplying, you turn into addition. So this would be the natural log of m plus n. So in terms of, it comes from the property of the exponential. So with the exponents, when you're multiplying like bases, you add exponents. So when I'm taking the natural log of something that's multiplied, I can equate that to turning into addition. Similarly, if multiplication turns into addition of the two terms, natural log of m plus the natural log of n, what do you think division, natural log of m divided by n, is going to turn into? Subtraction. This will be the natural log of m minus the natural log of n. And similarly, the natural log of m raised to the r power. Now, the m is being raised to the r power, and you're taking the log of it. That's that inverse property of a power to a power. You multiply. But to be able to multiply this r power, you got to stick him out front. So this will be turned into r times the natural log of m. So, in terms of log properties, these are your big three. Natural log of things being multiplied turns into addition. Natural log of things being divided turns into subtraction. And natural log of something to a power, you get to put the power out front and turn into multiplication. But I want to remind you, these are properties. This is an equation. I can go backwards and forwards. So if I want to, quote, combine logs, addition will turn back into multiplication, subtraction will turn back into division, and the power out front will go back into the exponent. Does that make sense? You can go backwards and forwards with this stuff. Now, other properties of logs, if you've got two logs equal to each other, the natural log of m is equal to the natural log of n, you pretty much can cancel the logs on both sides and get, if and only if, m equals n. Other properties. And they come from that exponential form I was talking about, the smiley face definition. What is the natural log of 1? In other words, the base on natural log is e. E raised to what power equals 1? E raised to what power? What kind of power can you have to always get 1 out of it? Well, we have a special power. What is it? 0. When you have a 0 power, anything to a 0 power is equal to 1. So in reverse of that, the natural log, or log of base anything, honestly, of 1 is always equal to 0. When you take the log of 1, you're always going to get 0. And it really didn't matter what the base is, but our base is e on this one. Now, here's the other one. What's the natural log of e? E, the base on a natural log, is e. So in other words, I'm really asking you, e raised to what power equals himself? What do you raise something to get the same thing back again? The first power. So the natural log of e will always be equal to 1. Properties, okay? Because the base on a natural log is e, and you got e. They basically cancel, and you're left with 1. So remember that. Natural log and e's cancel. So because of that, look at number h down here. I'll get the letter h here. What is the natural log of e to the x? As we just mentioned, natural log and e's are going to cancel, so we're left with x. This is log. The natural log of e to the x is x. Similarly, if I do it in reverse, and you talk about the exponential function, e raised to a natural log, they're still going to cancel, but this is the exponential form of that. E to the natural log. E and natural logs do what to each other? Cancel. So what are you left with? X. E's and natural logs cancel. So there's two ways you can cancel. The natural log of e to the x is equal to x, and e raised to the natural log of x equals x. Two ways the natural log and e are going to cancel. Okay? However, special note. Okay? There are no rules for simplifying this. The natural log of m plus n and the natural log of m divided by the natural log of n. These two guys are not the same thing as these two guys up here. Natural log of m plus n. You can't distribute logs. And this doesn't matter if it's plus or minus, actually. You cannot distribute logs. So that this is natural log of m plus or minus n is not the same thing as the natural log of m plus the natural log of n and the natural log of m minus natural log of n. These both terms have natural log on it. This is just one term with natural log. Pluses or minuses, you can't clean this up. They are what they are. Same idea with natural log of m divided by natural log of n, you can't clean that up. It is what it is. Now, the natural log of m over n, that's not the same thing. You can't factor out the natural log. So there's no factoring of natural logs. There's no distributing of logs is what we're really saying here. It is what it is. These are the only properties that you got. And again, we're focusing on this as a review. So, again, in the same light, let's take a look at this example here. It says this. If $6,000 is invested at 7.5% compounded monthly, how much will it take for the balance to double? All right, so this is a classic problem from your hawkstv.com, so make sure you guys go back and watch a similar problem on your Hawks TV. But here's the deal. Compounded monthly. I got this formula right here. A is equal to P times 1 plus R over N raised to the NT. My interest rate, R, is 7.5%, which, again, percentages for people who can't do math, 7.5% is 0.075. Compounded monthly, N is equal to 12, very good. How long is a question of time. We want to solve for T in this one. Now pay attention, even though I got to go talk about the rest of the numbers. Where is the T located on my formula? In the exponent. And there's only one thing in the universe that solves for exponents. That's logarithm. So this tells me I'm going to be using logs on this problem. But now the rest of it is this. You start out with $6,000. So what is your $6,000? That's your principal, which means what is the amount you're going to get back if you want to double it? $12,000. We're going to take $6,000. We're going to double our investment. We want $12,000 back. The question is, how long is it going to take? So I'm going to plug these numbers into my equation here. So I have 12,000 is equal to 6,000 times 1 plus 0.075 divided by 12 raised to the 12t. And the only variable left is t. All right. So watch what I do. First thing I'm going to do is I'm going to clean up. And I'm using order of operations. I'm going to clean up inside my parentheses. So I'm going to use my little calculator. And I'm just going to type up what is 1 plus 0.075 divided by 12. Just focusing on inside the parenthesis part. I end up getting 1.00625. So this equation turns into 12,000 is equal to 6,000 times 1.00625 raised to the 12t. Now, we want to solve for t. It's in the exponent. You can't distribute, you can't multiply this stuff because this guy has an exponent on order of operations. We work inside the parentheses first, then comes exponents. Then comes multiplication, division from left to right. Then comes adding and subtracting from left to right. Order of operations. So the next order of operation would be exponent. So since the t is in the exponent, we're doing algebra here. You got to get the variable or the term with the variable by himself. So my first move is to get the term with the t in it by himself. My first move is divide by 6,000. Get that 1.00625 to the 12t by himself. What I do to one side, I do the other. So I'm going to divide by 6,000. And when I divide by 6,000, 12,000 divided by 6,000, it shouldn't be a big surprise. What is it? I'll try again. Divide. 2. Not 2,000. It's just 2. You're doubling your money. All your zeros end up canceling, by the way. It's 12 divided by 6. 2 is equal to 1.00625 raised to the 12t. Now you've got the term with the t by himself. And there's only one concept in the world that solves for exponents. What is that? Logs. And we're going to be using natural logs in all the problems we're going to do. So we're going to take the natural log. But it's a function. So what I do to one side, I do to the other. So now I'm going to take the natural log of both sides. This will give me the natural log of 2 would be equal to the natural log of this 1.00625 to the 12t. Does that make sense? But now, we're going to use our log properties. The reason why you want to take a natural log is, with your log properties, where do exponents get to go when you take a log of something or other? Property number 3, it goes in front of the log. So, this will turn into, the natural log of 2 is equal to the exponent goes out front. That'll be 12t times the natural log of 1.00625. And then the last thing I'm going to do is I'm going to solve for t. What are you doing to this t that you're trying to solve for? We're multiplying it by 12, and we're multiplying by this weird natural log of 1.00625. What gets rid of multiplication? Division. I'm going to divide both sides by a 12 and a natural log of 1.00625. Divided by 12 times the natural log of 1.00625. This 12 will cancel here. The natural logs cancel here. And you're left with t. And I'm going to stick this on my calculator with parentheses around that large exponent. So this gives me the natural log, ln, natural log of 2, those parentheses divided by parentheses, because you got lots of stuff in the denominator, 12 times the natural log of 1.00625, close parentheses on the log, close parentheses for the denominator, and I end up getting 9.27081354 what? Years. Now, did they round it? Did they say anything about rounding? Yeah. Okay, fine. Give them all the decimals. You want to know how long it's going to take you to double your money? 9.27081354 years. Yeah, 9.27 years. About 9.25 years is what it's going to take. But your $6,000 will be $12,000 in 9.27 years. Does that make sense? All right? So the goal of this section is to get you that, remind you, as a review for us, remind you of your exponential and logarithmic properties on solving. So this is all about solving, because you know my next section's on take a derivative of this stuff. So take a look at these practice problems. Solve the equations for x. All right. Here's the deal. I got the natural log of x plus 4 times x plus 1 minus the natural log of x plus 4 is equal to 9. Natural log of 9. The first rule you want to do when you got, this is what I call a type 2 log equation. I got logs everywhere. I got logs on one side equal to logs on the other. The first rule when it comes to logs is combine logs. Combine your logs. Now, we got properties. So we're working backwards. Addition turns back into multiplication, turn into one big log to combine logs. Subtraction turns back into division, and coefficients in front of the logs go back into the exponents when you want to combine logs. So we're working on our log properties the way we've written them backwards. So that's a minus. So what is subtraction going to turn back into? Division. So this will be the natural log of x plus 4 times x plus 1 divided by x plus 4, combined log, equals the natural log of 9. Does that make sense? I'm using log properties. Subtraction turns back into division. You got to know your log properties. Now, you can clean this up. What cleans up? What's x plus 4 times x plus 1 divided by x plus 4? What cancels here? X plus 4 is canceled, so that just go ahead and clean it up. This would be the natural log of x plus 1 would be equal to the natural log of 9. Does that make sense? Now, we had another property. And that other property is this. When you got log of something or other equals a log of something or other, what can you do with your logs on both sides? Once I get a log of something equals the log of something, what do we do with our logs? They cancel. We can cancel the logs. This cancels with this one. What I do to one side, I do to the other. Officially, I'm raising e to both sides, but fine. But you can cancel the logs as the end result here. And you end up getting x plus 1 equals 9. And now solve for x. What you're going to do? Subtract 1 from both sides, and you get x equals 8. Does that make sense? However, one last thing about log equations. Listen up and listen good. When it comes to log equations, because you have that domain restriction that you can only take the log of positive numbers, you always have to check your answer. I'm not checking behind you to make sure you did the math correct. I'm checking behind you to make sure you don't have what we call an extraneous solution. But you get an answer, x equals negative 27. Circle it, no. But when you go back and plug it into the equation, you can't take the log of a negative number. It's a violation of the log properties. Does that make sense? So 8 is my answer, but I'm just going to go back to the original problem and just plug in 8, making sure I'm taking the log of positive numbers just to make sure it's legitimate. 8 plus 4 is 12. 8 plus 1 is 9. And 9 times 12 is 108. So that's nice and positive. That's all I care about. 8. 8 plus 4 is 12, and 12 is positive, so this is a good answer. Just mentally, just go back and plug it in. But if you get a negative number, natural log of negative 5, sorry, the answer is no solution. You cannot have that guy as an answer. You got to check your answers with logs. Take a look at this next guy. I've got e raised to the x minus 8 equals 133. Where is the exponent located? It is in the exponent of an e. There's only one thing in the universe that brings down exponents, and that's logs. And not just that, when I got an e in the problem, I'm always going to use that special log. Which log is that? Natural log. So the first move I'm going to do on this problem is, since I got that e by himself, I can kill him off by taking the natural log of both sides. So what I do to one side, natural log of e to the x minus 8, I do the other, equals the natural log of 133. Now, e and natural logs do what to each other? Cancel. That will leave you, and the exponent pops down front. That'll be x minus 8 is equal to the natural log of 133. Now, natural log of 133 is nothing but a number on your calculator. It's going to become crappy decimal. Just leave them alone. Solve for x. I got x minus 8 equals natural log of 133. What gets rid of that minus 8? What am I going to do? I'm going to add 8 to both sides. That'll give me x is equal to the natural log of 133 plus 8. Does that make sense? And that's perfectly fine. If they say they want you to round the answer to a certain number of decimal places, then in that case, I'm going to put it on my calculator and see what the decimal is. So this would be the natural log of 133 plus 8, and it's approximately, and we use the famous squiggly, equal to 12.89034913. And obviously there's more decimals behind it, and then you can go and round it to how many decimals they would like you to have, your choice. Or their choice, actually. Does that make sense? Okay? Take a look at this one here. Use properties of logarithms to rewrite the following expressions as a single logarithm. Okay? All right. The nice thing about logarithms I like to call is the Humpty Dumpty property. You have the ability to put Humpty Dumpty back together again when he's broken into many pieces, and you got the ability to bust him up when he's one big log and you want to have lots of little bitty logs and stuff. But this one, they want to combine to make one big log. Your log properties are very simple. The natural log of m plus the natural log of m is equal to the natural log of m times n, putting it back together again. And the natural log of m minus the natural log of n is equal to the natural log of m divided by n. But to be able to combine logs, listen up, the coefficient in front of the logs must be a 1. You can't combine a log unless the coefficient in front of that log is a 1. We got numbers in front of our logs. We got 5 natural log of x plus the natural log of y. There's a 5 in front of that natural log of x. Well, I got to get rid of it. Well, if you got a coefficient in front of a log, where did he come from? Put him back there. Where does he go back to? Exponent. So this gives you the natural log of x to the 5th plus the natural log of y. Now the coefficients are understood to be 1s in front of my logs. Now I can combine logs. Addition turns back into what? Multiplication. One big natural log of x to the 5th times y. That is my answer. Using my log properties. Does that make sense? Question. But you've got to make sure, rules, before you can combine logs, the coefficient in front of those logs must be a 1. So, here's another one. The natural log of x squared plus 7x plus 10 minus the natural log of x plus 2. Well, what's the coefficient? Again, directions say combine logs to write it as one big log, okay? Single log. What's the coefficient from my logs? Understood to be what? 1. So subtraction turns into what? Division. So the answer is going to be the natural log of x squared plus 7x plus 10 divided by x plus 2. But, of course, they do want you to clean this stuff up. And when I see a quadratic, especially in a fraction form here, I want to factor it, just to make sure. So this would be the natural log of, how does x squared plus 7x plus 10 factor? This would be x plus what? X times x. What times what is 10 that adds up to be 7? 5 and 2. You got it. And it'll be x plus 5 and x plus 2. But it's divided by x plus 2, and this is all inside your parentheses. So what happens to your x plus 2s? They're going to cancel. So you're going to get a cleaned up answer of the natural log of x plus 5. Does that make sense? Again, using the log properties and then just polishing it up. Take a look at number 3 here. Number 3 asks you to use properties of logarithms to expand 5x squared minus 45x plus 90 as much as possible. Simplify. Any numerical expression can be evaluated without a calculator. Okay, so this basically wanted to clean up this particular function here. Now, the problem is I've got the natural log of 5x squared minus 45x plus 9. Log properties state that multiplication turns into addition, division turns into subtraction, and powers get to go out front when you want to, quote, simplify and bust up and write as multiple logs, okay, using my log properties. I cannot distribute log. I can't do it with these pluses and minuses inside what I'm taking the log of. I can't touch this stuff. So what I want to do is, you see this quadratic? I want to turn it into multiplication and or division, in this case multiplication. The first thing that I notice is I got a 5 in common in all my terms. I can factor the 5 out. So this would be the natural log of 5 times, now 5x squared, factoring out the 5 leaves me with an x squared, minus, factoring a 5 out of 45 is what? Makes me have a 9x plus, factoring a 5 out of 90. What would factoring a 5 out of 90 be? 18. 5 times 18 is 9. 18. So I just factored up 5. Does that make sense? Now I've got my quadratic in a little better form. Now I'm going to try to factor the quadratic. So this would be equal to the natural log of 5 times, and I'm going to factor the quadratic. X squared minus 9x plus 18. X squared factors into x times x. What times what is 18 that adds up to be 9? What times what is 18? Let's see. Factors of 18. Let's go through them. 18 is 1 and 18, 2 and 9, 3 and 6. I think that's about it, right? So which one of these guys is going to add up to be 9? 3 and 6. 3 and 6. And what do my signs have to be? Because it's plus, they're going to have the same sign. Because the middle term is minus, the same sign they're going to have is minus for both of them. Does that make sense? Now, let's finish this problem up. Even with a constant, I have taken my quadratic that we're taking the log of and turned it into multiplication. It's the natural log of 5 times x minus 3 times x minus 6. Multiplication turns into addition. And this 5, constant as well, is being multiplied. So breaking it up, this will be the natural log of 5. Addition, multiplication turns into addition. That'll be plus the natural log of x minus 3. Multiplication turns into addition plus the natural log of x minus 6. That's what it's equivalent to in its log property format, including the natural log of 5. A lot of people kind of try to leave the 5 in there. Nope, it's being multiplied. You can turn that into addition too. It's just a constant. Okay, so here's another problem. How long does it take $3,850 to double if it's vested at 8% compounded continuously? Round your answer to 2 decimal places. All right. So how much money are we investing? My principal is $3,850. The interest rate is 8%, but again, percentages for people who can't do math. 8% is 0.08. Compounded continuously means I'm going to use what formula? A equals hert. Very good. Knowing your formulas, compounded continuously tells you the formula which you use. And we want to double. Double, the amount back is going to be, well, time for a calculator now. Let's see, here we go. I got $3,850, and we want to double that times 2, makes it $7,700, $7,700. So, $7,700. And the question is, how long is a question of time? So you notice how we attack word problems. We read through the word problem, we read through it again, pulling off the numbers and identifying who they are, identifying which formula I need to use, and then figuring out who I need to solve for. Somebody's got to solve the answer. I got to find the T. So now plugging into my formula PERT, A is 7,700 is equal to 3,850 e to the 0.08t. Where is that t located that I want to solve for? It's in the exponent of an e. And the only way it's going to kill off an e and bring down an exponent is logarithms, natural logs. But I got to get the e by himself. So what is my first move in terms of algebra to be able to solve for that t? What's my first move? Got to divide. Got to divide by 3,850 on both sides. What I did to one side, I did the other. This cancels. 7,700 divided by 3,850 is, what's the price? 2. Actually, you doubled it. Equals e to the 0.08t. Now you got the e by himself. What kills off e's and brings down exponents at the same time? Take the natural log of both sides. And the natural log and e are going to cancel. I'm just going to write it this way to help you out. This will be the natural log of 2 is equal to, the exponent pops out front, 0.08t. And then what's your last move to solve for t? Get that t by himself. Divide by 0.08. So this gives me t is equal to, and then putting it on my calculator here, natural log of 2 divided by 0.08 is 8.664339757. But in terms of an answer, they did say they wanted me to round the answer to how many? 2 decimal places. So 2 decimal places would be here, so the answer is 8.66, and it's a word problem, so you got to tell me units. 8.66 what? Years. One more. $8,650 is invested at 5.5% compounded continuously. How long will it take the balance to reach $17,300? Round your answer 2 decimal places. All right, so we're investing P, $8,650 at an interest rate of 5.5%, which is 0.055, moving my decimal place 2 places to the left on the percentage. How long is a question of time. Will it take the balance, so our amount wants to be $17,300, okay? And they mentioned the famous words compounded continuously, which means I'm going to use my famous A equals PE to the RT formula, compounded continuous formula. Have it memorized. Plugging the numbers into my equation, this will give me $17,300 is equal to $8,650 times e to the 0.055 t. Solving for t, it's in the exponent of an e. What's my first move? I'm going to divide by 8,650. This will cancel. Grabbing my handy dandy calculator, $17,300 divided by $8,650 makes it 2. It actually doubled my money. E to the 0.055t. Again, what I'm going for is the pattern on this stuff. What is my next move? Take the natural log. You've got to kill off that e, so you take the natural log of both sides. This will cancel, running my equation this way. That'll give me the natural log of 2 is equal to 0.055t. And then what's your last move? Divide by 0.055. Get this t by himself. This cancels. Leaves me with t equals natural log of 2 divided by 0.055. And I get 12.60267601. But to answer their question for that 2 decimal places thing here, 2 decimal places would be 12.60 would be my answer. 12.60 years. Does that make sense? Now again, this whole goal on this stuff, honestly, is review. The real important stuff is section 5.3. Section 5.3 is on differentiation of these functions, the exponential and the logs. So, getting you guys started on this. This is the important part of this whole lecture here, is this part here. So, differentiation. We're going to be focusing on 2 different functions. The first function is this, y equals e to the x. This is your exponential function. And the other one is y equals the natural log of x. These are 2 special functions, and we're talking about taking its derivative. So the dy over dx, or y prime, would be equal to, and here's the beauty of it. The reason why this e, 2.7182818 number, shows up in nature naturally, called the natural number here, is because of this reason here. Now, when you sit there and look at the limit properties and these and analyze science and things around you, this is another one of those God-given numbers that just shows up when you study it. When you study nature and science and physics and the like, as well as it also applies in your business concepts. But here's the reason. The derivative of e to the x is e to the x. It's the only function in the universe besides 0 gets its own derivative. The derivative of e to the x is e to the x. So when you have things growing at a rate proportional to themselves, e to the x keeps showing up. And now a lot of things in science and nature do this. So that's why this 2.71828 number is very special. However, remember, there's two rules of every kind of rule we're going to give you from this point on. There's the basic rule. You know what derivative of e to the x is? It's e to the x. Then there's the chain rule version of it. If you got y equals e to a function, something other than just plain old x or t or whatever the variable is, this is the chain rule version of it. Y equals e to a function, the derivative, your dy over dx or y prime is going to be, derivative of e to a function is e to the function, but then you got to do times the derivative of the exponent. The derivative of the exponent, what's the derivative of f of x? Is going to be times f prime of x. This is the chain rule version of this formula. Derivative of e to the x is e to the x. Derivative of e to a function is e to the function times derivative of the exponent. Now, compare that to the natural log function. The derivative of the natural log function, dy over dx, to give you a little Leibniz look to it, or y prime, that is equal to, the derivative of the natural log of x is 1 over x. So the derivative of natural log of x is 1 over x. Derivative of natural log of t is 1 over t. Okay? But with that, you also have the chain rule version of this guy. So what you need to remember here is this 1 over when it comes to logarithms. So if I got y equals the natural log of a function, something other than x, then your derivative, dy over dx is going to be equal to, which is y prime is equal to, well, derivative natural log of x is 1 over x, but derivative natural log of a function is 1 over the function. Then you got to do chain rule, times the derivative of the inside. Now, I like to write the rule like this, but some teachers will sit there and go, well, it cleans up to become f prime of x over f of x. And you're right, it does, but you're missing the point. The goal is to memorize these forms. So derivative of e to the x is e to the x, derivative of e to a function is e to the function, catch the pattern, times derivative of the exponent. Derivative of the natural log of x is 1 over x. Derivative of natural log of a function is 1 over the function times derivative of the function. But when you clean it up, it does make the derivative go into the numerator stuff. But that 1 over is the trick on the natural logs, okay? Because we're going to be calculating these rates of changes of these problems. And you guys know, when it comes to rates of change, you know you're going to be taking the derivative. Study hard on this stuff, and I'll see you guys on Monday when we finish up 5.3 and 5.4. And who knows, you may have a next test next week or something. Study hard. See you guys then.